Good morning, advanced algebra students. I hope you are doing great. I am so happy to be with you again. We are going to be doing notes for 1.2. So we are now officially into our advanced algebra book, chapter 1. The topic that we're talking about today is called transformations of functions. Now this can be a little bit confusing to think about unless you have concrete examples to work with, and we will. But basically, this section of the book is going to teach us patterns that we are going to see in a variety of functions throughout the year, ways that functions can be moved, and how we can describe that movement. So let's just go ahead and jump right in. And again, I'm just going to streamline things for you and write the basics on the board, and I'll read you the rest. So in lesson 5.1, we learned how to transform the parent function y equals absolute value of x. So let's just kind of review what that graph looked like. And again, we can either call that y equals absolute value of x or f of x equals absolute value of x. When we graphed that function, we could see that it was a V shape. That's the basic parent function. Now, if we would like to see how that would compare, let's call this example 1, with another function, let's take a closer look. Let's look at the function f of x equals 1/3 times the absolute value of x minus 1 plus 2. So we did discuss how to graph this. First, we look for the vertex. The vertex is at +1, +2. Remember, there's a minus sign built into the formula there. And then we count out the slope of the right-hand side. So we would have 2 symmetrical branches here. Now, this part that I've just done on the board is not new. But what I would like to talk about is some more vocabulary on how to describe what we did. So we can say that the parent function has been translated. So we're going to say translate 1 unit right and 2 units up. Notice that 1 and 2 correspond to the x and y coordinate of the vertex. So in a translation, each point on the parent function is shifted left or right and up or down. So that was part of what happened here. But notice that the function has also been shrunk. It's not quite as tall as it used to be. So a compression is a transformation that decreases the distance between the points of a graph and the given line by the same factor. So this graph here is a compression of the parent function. In this example, the factor was 1/3. So we're going to say that this was shrunk by a factor of 1/3. And notice that 1/3 is the number that we see here. Okay, so I'd like to do one other example like this, and then we'll write some generalities on the board. So that was example 1. Let's look at example 2. For example 2, we're still looking at the parent function, y equals absolute value of x, or f of x equals absolute value of x. Now we're going to consider -2 times the absolute value of x plus 1. So let's go ahead and graph this, and you can see why it was so essential that we did a little mini unit on graphing absolute functions before we dived into this chapter. Okay, so let's see what's going on here. The way that we would want to describe this transformation is we would say that the graph has been translated 1 unit left and then it has been stretched, not shrunk this time, but stretched by a factor of 2. notice that we get the 1 here next to the x and the 2 there. Now something else has also happened, and that is that the V shape has been flipped over the x-axis. So we're going to say it has been reflected across the x-axis. And we get the reflection aspect of this transformation from that minus sign. So I'd like to give you some general, this will be example 3. It's not really an example, I suppose, but just some general ways of describing these transformations. If we want to talk about a horizontal translation, 1 unit right, f of x becomes g of x equals f of x minus 1. So anytime that we see a minus 1 next to an x in the parentheses, that means a translation 1 unit right. If we want to talk about a vertical translation up 2 units, then f of x would become g of x, which would be f of x plus 2. So when you see the plus 2 not in the parentheses with the x, that means that we're going up by 2. If we want to talk about reflecting a function across the x-axis, then f of x becomes the opposite of f of x. So there would be a minus sign in front of the function. If we want to talk about a reflection across the y-axis, then f of x would become f of negative x. If we want to talk about a vertical stretch by a factor of 2, then f of x would become 2 times f of x. And if we want to talk about a vertical compression by a factor of 1/3, f of x would become 1/3 f of x. So this is relatively new for everybody. If you're feeling a little uncomfortable now, that would be normal. Keep in mind we are going to do a bunch of examples of this in the homework, but it's really good that you are taking the notes because it will make it easier for you to understand what's going on in the homework. Okay, let's go ahead and look now at example 4. We can apply the same transformations that we used with absolute value functions to something called parabolas. Now, most likely you have not graphed parabolas yet. We're going to learn a lot more details about graphing parabolas in the next chapter. I'm actually really looking forward to it. For right now, we can graph a parabola using a t-chart. So let's say we wanted to graph f of x equals x squared. We could graph that by doing a t-chart using values from -2 to +2. And we can see that y is always positive because we're squaring. Y is just x squared. If we graph this parent function, we have the vertex at the origin. We have a point at 1, 1, and also at 2, 4. And then we've also got a symmetric branch going, flipping that across the y-axis. So that would be our parent function. Now, let's see how we would graph that same parent function with a slight change. So let's write this out. F of x equals x squared plus 3. Can you look back at the general instructions that we just finished writing and tell me if f of x looks like this picture here, what would f of x plus 3 be? Which is essentially what that is. What does that plus 3 tell us? Notice that this plus 3 is not in a parentheses with x. So if you looked at your notes or you remember what we said, you should notice that this will have the effect of moving the whole graph up 3. So we aren't changing anything else except for moving it up 3. So we would say that it has been translated 3 units up. Let's talk about the domain and range of these. The domain of the parent function is all real numbers. we can write that as a capital R with 2 bars on the left. The range is just that y has to be positive, so y greater than or equal to 0. Let's see how that compares with the domain and range of this function, the parent function, when it's been transformed. Our domain, or all our possible x values, is still going to be all real numbers. However, can you tell what happened to the range? Instead of y being greater than or equal to 0, what is it going to be? It's going to be y greater than or equal to 3. Good. Okay, we just got a little bit more. You guys are doing great. The next example says to write a parent function, or no, to write a function g if the parent function is, so let's call this example 5. If the parent function is f of x equals x squared, we are to write what the function would look like if it has a vertex at 3, -6. So this is where you want to use the general guidelines that we talked about before. Notice that this 3 in the x spot means we have to shift to the right 3. And this -6 is telling us to go down 6. So we would write g of x equals, in parentheses, x minus 3 squared, and then -6 outside the parentheses. Notice that this 3 is negative because of the minus sign already built into the formula. Okay, let's go ahead and do, let's say, 2 or 3 more examples. So this was example 5. Let's look at example 6. With example 6, we're going to graph the function as a vertical stretch or compression of the parent function. So if g of x is equal to 0.5 times the absolute value of x. Now, something you should know is when the number that stretches or compresses the function, the number in front of the absolute value sign here, or the parentheses in the other example, when that number is between 0 and 1, it's going to shrink it. When it's greater than 1, it's going to stretch it. So what happens in this example here with the 0.5 in front of x is it's going to shrink with it's going to have a vertical compression with a factor of 1/2. So we're still going to have the vertex at the origin, but instead of going up 1 over 1, we're going to go up 1 over 2. It might be easier to visualize this writing it 1/2 times the absolute value of x. So we're going up 1 over 2. So we would say a vertical compression, or shrinking it would also work, with a factor of 1/2. Okay, let's do another example. Example 7. What transformations of f of x equals x squared are applied to function g? So let's go ahead and make this example 7. The question is, what are the transformation? So g of x is the quantity x minus 4 squared plus 7. So what have we done to the parent function, which we can call f of x equals x squared, to get g of x? If we look back to the general rules that we wrote down, we can see that the 4 next to the x is going to translate the function 4 units right. And then the 7 on its own is going to translate 7 units up. You guys are doing awesome. Okay, I'm going to do one more example. I know this has been really fast. Hopefully you've been hitting the pause button a lot. Example 8. G of x is equal to negative x squared minus 4. Now for me, I'm super visual. I find this a little bit easier to understand if I write it as negative 1 times the quantity x minus 0 squared minus 4. Notice that there is no shifting left or right here, but we are moving 4 down. So we're going to say translated. It's been translated 4 units down. What do you think this minus 1 out here does? The minus 1 outside the parentheses means that the graph has been reflected across the x-axis. All right, I know that was pretty intense. I'm really proud of you if you hung in here till the end. I hope you have a good day. See you soon in Zoom.